All right, today we are diving into one of chemistry's coolest and honestly most elegant concepts, synergic bonding. It's this unique kind of chemical partnership that explains why whole classes of molecules are so incredibly stable. Let's get right into it.
So let's start with a question. We usually think about chemical bonds as a pretty simple transaction, sharing electrons, maybe one atom taking them from another. But what if it was more dynamic? What if it was more like a conversation, a mutual exchange happening in real time? Well, that's exactly what we're talking about with synergetic bonding.
So here's our game plan. First, we'll nail down exactly what synergetic bonding is. Then, we'll meet the key players involved in this little dance. After that, we'll walk through the mechanics of this electron two-way street, see the surprising domino effect it has, and finally, wrap up with why this whole concept is so darn important.
Okay, let's get right to it. What is synergic bonding, really?
Okay, here's the textbook definition, and yeah, it sounds a little heavy at first, but stick with me. Just focus on those two key phrases, donation from a ligand to a metal, and back donation from the metal to the ligand. See that? Electrons flow one way, and then they flow right back. It's a perfect self-reinforcing loop. Really, the absolute best way to think about this is as a cooperative give and take. It's not a one-sided deal at all. Both partners are giving something, both are getting something back, and the whole connection gets stronger because of it.
All right, so for this chemical dance to happen, you need two very specific partners. Let's meet them.
First up, you've got your transition metal, and it's just perfectly suited for this role because it can do two things. It has empty rooms, vacant orbitals, ready to accept electrons, but it also has full rooms, filled d orbitals with electrons it's happy to donate. Then you have the ligand, and a classic example is carbon monoxide. It also has a dual personality. It's got a pair of electrons ready to donate, but it also has these special empty orbitals, we call them anti-bonding orbitals, that are ready to accept electrons right back. So you see, both partners are perfectly equipped to both give and receive.
Okay, we've got our dancers on the floor. Now let's watch the actual steps of this two-way street. So this all happens in two key steps, and they're happening pretty much at the same time. First, the ligand makes the first move. It donates its electron pair to the metal, and this forms a pretty standard bond we call a sigma bond. That's lane 1 of our highway. But then, almost instantly, lane 2 opens up. The metal gives back, or back donates, pushing electrons from one of its full orbitals into that empty orbital on the ligand. And this forms a second, different kind of bond, a pi bond. One gives, the other gives back. It's that simple. And this, right here, is why we call it synergic. These two steps aren't happening in isolation. They actually feed each other. The more electrons the ligand gives to the metal, the more electron-rich the metal becomes, which makes it even better at giving electrons back. It's this beautiful, self-reinforcing cycle that makes the whole thing incredibly stable.
So you've got this constant back and forth, this electron superhighway. But so what? What does it actually do to the molecule? Well, this exchange kicks off a really fascinating and totally predictable domino effect.
This isn't just some theoretical idea, you know? This give and take has real physical consequences that we can actually see and measure. It physically changes the bonds involved.
And this table lays it all out beautifully. Look what happens. First, the bond between the metal and the ligand, the ML bond, it actually gets stronger and shorter. That makes sense, right? It's basically a double bond now. But here's the really cool part, the trade-off. The bond inside the ligand itself, like the one between the carbon and the oxygen, it gets weaker and longer.
Okay, so why does this happen? It all comes back to where those electrons from the metal are going. Remember, they're going into the ligand's anti-bonding orbitals. And the name says it all. When you put electrons in an anti-bonding orbital, you are actively working against the bond. You're weakening it. So it's this amazing trade-off. To get a stronger connection to the metal, the ligand has to sacrifice a little bit of its own internal strength.
All right, we've been deep in the weeds with orbitals and bonds. Let's pull back and look at the big picture. Why is this so important in chemistry? Why does it matter?
Well, it's a huge deal because this idea, it's the key that unlocks the mystery behind the stability of a whole really important class of compounds called metal carbonyls. These things are all over the place in industrial chemistry. They're used as catalysts, and honestly, without synergic bonding, they just wouldn't be stable enough to exist. It's the missing piece of the puzzle.
All right, let's wrap this up with the key takeaways you absolutely need to remember. First, synergic bonding is a two-way street.
a sigma donation from the ligand and a pi back donation from the metal. Second, this process makes the bond to the metal stronger. Third, at the same time, it makes the bond inside the ligand weaker. And finally, this whole give and take is what explains why so many important chemical compounds are so stable.
So, I'll leave you with this one last thought. This principle of a mutually reinforcing give and take, where two parts strengthen each other through exchange. It's a really powerful idea. Where else do you think we might see that? Maybe in biology, in ecosystems, maybe even in things like economics. It's something to chew on. Thanks for diving into this with me.